Hi, my name is Joe Alexandersen, and I'm an assistant professor at the Department of Mechanical and Electrical Engineering at the University of Southern Denmark. Today, I'll be revisiting the optimal thickness profile of cooling fins, and I'll be doing so using optimality conditions and further exploring branching that some of these theoretical models predict. So the first question I want to ask is, what is the optimal topology for heat sinks? And this is what my research work has been centered around for the last few years, using topology optimization to generate heat sink geometries for certain applications. But how should they actually look? So there's a lot of we have these very simple geometries that we often see in practice, cheap to manufacture. We have Bayesian's constructal theory predicting these tree-like structures, which we also very often see within topology optimization. But the question is, what is the best way to do this? And what we'll be sort of focusing on today is what is the actual profile of these fins? So what is the cross section of these fins? The second question I want to ask is, and that's actually what started this sort of more theoretical work that I've been doing, is are topology optimized heat sinks for heat transfer, cooling of a heat source actually inherently castable? So this is based on what we've seen in experience. We've seen both from simulations, but also actual castings, really, really nice solidification behavior. And we see very, very low porosities. So we kind of wanted to see if we can analytically sort of try to understand what's going on here. So when we're talking about heat sinks here, it's very important to talk about which kind of heat transfer mechanism we're dealing with. So let's start with diffusion. So that would be a stagnant fluid or two solids. And that's what we have here. We have a highly conductive medium in the black, and then the white is a low conductive medium or a stagnant fluid. So for this case, despite this constructal theory actually being very popular and people in the topology optimization literature often comparing, oh, we have these tree-like structures, they must be optimal, and we see these a lot, it actually turns out that laminar needle-like fins with no branching are optimal in pure conduction. So it turns out that these branching structures are actually poor local minima that are sort of due to the local in time and local in space phenomena here. And you can read more in their paper about that. So we also observe these branching structures a lot in conjugate heat transfer. So I've primarily worked with natural convection here, where we have buoyancy sort of driving the flow. And we see these sort of very organic coral-like structures and these sort of tree-like structures here for different passive coolers. But the question is, are these truly optimal, or are they just local minima that we fall into, just like in the conductive case? We don't really know yet, and I don't have an answer here, but it's worth investigating. So the sort of classical results, if we just look at a single heat fin and look at the profile, so if we look at the cross section of one of these straight fins here, we get sort of the classical Schmidt-Duffin profile. And this is a quadratically tapered profile that was first postulated by Schmidt in 1926 and later proven by Duffin in 1959 more rigorously and mathematically. And this is based on the sort of Schmidt came up with the postulate that the flux should be constant throughout the fin based on a one-dimensional heat transfer analysis. And that's what Duffin sort of ran with and proved the optimal solution is a quadratic taper. However, in 1987, Snyder and Krauss discussed the lacks of this model. So this is based on assuming an assumption of the length of the arc is negligible, so that the taper here does not add to the heat transfer area, which it of course does in practice, but we assume it's small. And if you include it, we actually get ill-posedness of the mathematical problem. We get oscillatory solutions and an unbounded heat transfer principle. We can add infinitely many, infinitely small oscillations, and we get infinite heat transfer. This was revisited in 2014 by Gilles-Marc et al., and they analytically proved non-existence when you include this length of the arc. These papers are very hardcore mathematical by mathematicians mainly. And me as an engineer coming to these, like I said, we had a curiosity we had served. We wanted to try to understand. So we looked at what had been done so far. don't really understand the reasoning here. It's sort of mathematical tricks leading to these sort of observations and analytical results. So we wanted to sort of approach it from our point of view using optimization theory, namely Lagrangian optimization. And you could say this is still hardcore mathematics, but actually the solution arises from optimality conditions. And these come from stationarity, which is something most people can relate to. We know that the minimum of a function is where the gradient is equal to 0. So these sort of ideas is what we tried to use. So we have our fin equation here, our fin problem here. We have a heat source at the bottom. We have convection on the two top and bottom surface, and we have some thickness that can vary in the x direction. We assume that it's very deep out of plane. We have a relatively long compared to thick fin, so we can reduce it to a one-dimensional problem where only the temperature only varies in the x direction. We introduce the temperature excess theta, and we get this 1D heat equation for the temperature of this heat fin. So this has been arrived using this length of arc assumption that we can neglect. So we assume that the length of this side here is equal to the width of this element. So essentially we're saying that the gradients of the thickness is relatively small. So we get that we can neglect this additional term here. And that's what Schmidt and Duffin did as well. So we pose our optimization problem. We seek to minimize the functional here, which is thermal compliance. So it's essentially the temperature at the base. We have our governing equations as constraints. And we also say that the thickness integrated up over the length should be equal to some predefined area that we specify ahead of time. We then form our Lagrangian function. We require stationarity with respect to all the variables, and these lead us to our optimality conditions, which are seen here. So the first one is that our problem is self-adjoint. I won't go into details here. You can read in the paper. This is due to the choice of the objective functional. We get that we have a constant heat flux or a linear temperature profile. We see that we have a linear thickness gradient, so that would be a quadratic thickness function. And we have that the length of the fin should be long enough such that the temperature excess reaches 0 at the tip. So if we made it longer, we won't dissipate additional heat. If it's too short, we won't dissipate all the heat. So we want the length to be such that the temperature at the tip reaches the ambient. So from these conditions, we can derive the optimal solutions that we see here, and those we can compare to those by Duffin, and they're exactly the same. So if we then try to visualize them here, we see here, this is for aluminium, so 200 watts per meter per Kelvin for the conductivity. See for different convective heat transfer coefficients. See as we increase the convection, the length of the fin is shorter and it gets wider, and we clearly see this quadratic taper in the profile. The temperature field is clearly linear, and we go from some base temperature, which of course falls as we increase convection, but then linear down to 0 at the tip of the fin. So this is all what we already know essentially from the other papers, but now derived in terms of an optimization problem. But what happens if we include this length of arc, so the taper-dependent surface area? So we include this term, we don't neglect this gradient term. Well, like I said, Snyder and Krause and Mark all showed that this is an ill-posed problem. It's analytically unbounded. And if we look at it numerically, we can see that we get highly oscillatory solutions. So the black lines here are the traditional quadratic taper, and the blue is the numerically obtained. Here we've set a limit to how wide it can get, because in principle it wants to get infinitely wide. So if we require it to be more or less the same thickness as the original one, we get more oscillation, slightly longer, because we need a slightly longer fin to get more lateral surface area or vertical surface area. And if we let it go to infinity, you essentially get an infinitely short and infinitely wide heat sink or cooling fin, because we can just get rid of the heat using only vertical area. If we go to 2D, so this was a 1D or 1.5D model, we can go to 2D, and in topology optimization, we see very similar issues. We see these very small features, see dense networks, we see oscillations in the design, and these are essentially the same problem. There's these oscillations in the problem, and they come because it's an ill-posed problem. So essentially, the optimizer just wants to maximize the surface area on which the convection arises. So, but if we look at how these fins actually perform, or going out from 1D analysis or 1.5 to 2, we see that they do predict better heat transfer for these oscillatory fins here. So we see a quite low temperature compared to the quadratic taper here. But if we analyze them in 3D, we see that the quadratic taper fin is actually better. So this is for natural convection, the same heat input into all three of these fins. And we, of course, see that we get very different temperature profiles, and we actually see that our two oscillatory solutions are worse than the classical solution. So it might be in practice, we don't need these highly oscillatory solutions. And that is, of course, because in principle or in real life, if you have very, very small spacings between your fins that these oscillations represent, you get not a lot of fluid passing through these spacings, and thus not a lot of heat transfer. And you can actually see by looking at the surface convection coefficient that they are very low in between these oscillatory peaks here, these additional fins that are in the other direction. And that's actually why it's not necessarily better to have in real life than the actual quadratic fin here. So all of these problems are caused because we have a design-independent convection coefficient. We have just Newton's law of cooling, no flow model, and we have a convection coefficient that is set to a constant. So we have a non-physical problem, an unphysical problem, so of course we have a lot of issues. Are these issues solved using a flow model? Yeah, but just expensive computationally, because we now need to resolve the fluid as well. But it's now more and more complicated. We have to treat it numerically. We might not get the optimal solution. So for passive coolers, we have a heat source down here, an electronics chip. Inside an enclosure, we're cooling the outer walls. We're allowed to place material in the gray box. And we see that for a diffusion dominated case, we do get these sort of long, slender, lamella-like fins conducting the heat out from the heat source. But as we increase the chip power or increase the dominance of natural convection, we see that we of course contract, because we now need to conduct the heat shorter in order to sort of transfer it to convection. Convection becomes more beneficial. This is a classical result, also seen in the length shortening of the analytical fin. But we actually see that the complexity increases, get more and more secondary fins and more tertiary fins. And again, the question is this actually optimal? Well, this one actually does perform very well compared to all of the others for these conditions, so there might be something to it. Question is, do we observe linear temperature fields? Kind of. So these points are the surface temperatures of this design here, and we see it actually does sort of macroscopically follow somewhat of a linear trend here. Of course, locally we do have something different than linear, but overall it does. So maybe there is something to this sort of classical result anyway. If we go to light emitting diode lamps, we still see these very complex branching structures, a highly non-constant H, which of course invalidates the sort of basic theory. But again, we see something that sort of resembles, we see this sort of kind of almost linear taper, and then with these oscillating fins on the side. So again, there must be some kind of connection between this, and that's what we're trying to find out here. Finally, like I said, the sort of starting point is castability. We observed that these structures just solidified really, really well, both numerically and experimentally. We looked into try to incorporate some common casting rule of thumbs into this sort of analytical framework. And we see essentially that as the convection decreases, we approach a linear profile. And this is sort of akin to essentially becomes a length constraint and a gradient constraint. And we very often see in topology optimization that we actually have some outer dimension constraints that might be part of what interacts with the volume constraint, interacts with other length scales, and of course the physics, to give us this sort of these sort of classical-ish profiles. But again, the connection between the simple analysis and the full 3D is still very difficult. It's not direct, so we haven't done that yet. Hopefully we'll be able to do something. And this is also, we are looking into solidification models because of course one thing breeds another. So this is another interesting area. We're looking at these tree type structures with respect to solidification as well. And with that, I'll finish with some references here, and you can always check out my website here, down here, joealexandersen.com, or using the QR code. Thank you for listening, and have a nice conference.